So what we saw in the first video of the shell method approach for finding the volume of a region as it's rotated around the X or Y axis essentially told us when we want to use the shell method when the disk or washer method becomes unwieldy or impossible to use, and particularly when there is going to be a separation between the region that we're finding the volume of as it's rotated and the axis of rotation itself. And essentially what is created from those infinitesimally, small rectangles that we create, we essentially are creating a shell of a cylinder that we're trying to find the volume of. And when we unfurled the cylinder, when we kind of cut it apart and laid it flat, we kind of got a prism looking shape like what we see here, that the width essentially they kind of had it labeled as that was dx, the height was the f of x, and the portion at the bottom they kind of had that as the uh, circumference of the cylinder, which would be the 2 pi r. Now whether we are using a vertical or a horizontal axis of rotation, the method for the shell approach is essentially the same. The difference, of course, is that if I'm revolving around the x-axis, or I'm sorry, if I'm revolving around the y-axis for a vertical uh, revolution, here the interval is going to be on the x-axis, and we want to leave our functions essentially like they're given to us, where it says like y is equal to x squared, or y is equal to 4x minus x squared, or whatever the case was. The horizontal axis of revolution, where we're revolving something around the x-axis, this will give us our interval to be on the y-axis instead. And this is where you would need to take your functions and solve them in terms of x if you needed to. And this x here and this y here, didn't really locate that very nicely. This y here, those are essentially just the radii of whatever your cylinder is. So those are going to be given to you by the function itself, or by the problem itself. And the 2 pi, if you want, you could take either of these expressions, and you can take the 2 pi and have it pulled out as a constant. And then you would just say y times fy times dy, like that. And that's really how I'm going to be working out the examples, is I'm going to pull the 2 pi out as a constant. Okay, and here's just a little bit more extra information on that the rectangles that you're using are going to be parallel to the axis of rotation, kind of like what you see in the diagrams here. Let's go ahead and take a look at our first example. We have two examples that we're going to look at in this video. Find the volume of a solid revolution obtained by rotating the region bounded by the curve y is equal to x squared and lines x equals 1, x equals 2, and y is equal to 0. Now these two bits here basically tell me that we don't need the entire function. We could take the parabola and kind of go like that, but we really don't need the left side because, let me see if I can, there we go, actually hit the vertex there. Because the boundary is only going to be on the right side of the y-axis. Okay, so let's say that those are the two lines that are x1 and x2, and of course the y-axis itself makes up the, I'm sorry, the x-axis itself makes up the third line. So this point here, so the region that we're identifying is this region here as it is rotated around the y-axis. So this point here will be 1, 0. This point here is going to be 2, 0. For our The parent function of the quadratic here, when x is 2, y will be 4, and when x is 1, y will be 1. So we would need to identify those points to be able to identify the region or the interval correctly, depending on which way it's being rotated. But in this case, because it's being rotated around the y-axis, the interval is going to be on the between the x values. So in this case, the interval is going to be from 1 to 2, and that's going to make up what our defined interval is going to be. Now, let's go ahead and start figuring out what we're going to be plugging in to the function itself, or to the formula for how we're going to find the volume with the shell method. Now, what it gave you on the previous page was from a to b for our defined interval, we have 2 times pi times x. That makes up the cylinder, or not the cylinder, but the circumference, or one dimension of the 3 that we need for our volume, times f of x, which was the height, times dx, which was the width. Now, we've identified what the interval is going to be. Is going to be from a to b, and I'm going to pull out the constants 2 and pi. So this will be from 1 to 2 times x. Now the x again that's just the radius, so that's always going to be there. It's just going to be x. Now f of x in this case, the region that we're looking at is only going to be formed by this one function here, so that f of x is going to be the x squared curve times dx. And now we have our defined interval in order to be able to figure out what the volume is going to be. So at this point, go ahead and start working through the rest of the problem. So we have 2 pi from 1 to 2 for our interval. The integrand will simplify to be x cubed dx. And now we can start taking the antiderivative. So I'm going to say 2 pi times 1/4 x to the 4th, evaluated from 1 to 2. Now the 1/4 is going to be kind of a common factor between the upper and lower bounds when I use the fundamental theorem to find the volume. So I'm going to go ahead and factor out the 1/4 as a constant also. So 2 times 1/4 will be 1/2 pi, or pi over 2, however you want to write it. And now we can start plugging in the 2, so it'll be 2 to the 4th power minus 1 to the 4th power. So that gives us 1/2 pi times 16 minus 1. And so 16 minus 1 is just going to be 15. So 15 times 1/2 pi will give me 15 pi over 2 for the volume of this particular problem using the shell method. So now let's go on and take a look at the last example that we have in our notes. Find the volume of the solid of revolution obtained by rotating a region enclosed by a rational expression, y is equal to 2 over x, and a linear expression about the y-axis. Okay, so because we're rotating it around the y-axis again, we want to leave things in terms of y. So immediately the first thing I'm going to want to look at is I want to take this and put it in terms of y. So that's going to be y will be equal to negative x plus 3. So now I can go ahead and graph the functions. Well, the negative x plus 3 is going to be the easiest one to do. So that'll be kind of up here at a positive 3, and then it'll come down here with a slope of negative 1. So about 1, 2, and 3 here, and we'll just say that that's 3 there on the y-axis. And the rational function for this one is going to kind of have a downward curve like this. It's going to kind of come down like so and like so, something along those lines. And The region that we're looking to work with here is just this little bit right here. This is the region that we're going to be spinning around the y-axis. So we're still going that way. Now in this case, the interval is still going to be along the x-axis. The interval is going to be made up of the x numbers. So we need to find out, well, where are they going to intersect each other? Where is this point here? Where is this point here on the y-axis? Or at the very least, do they correspond with the 1 and the 2 down here? And I kind of drew it that way to allude to it, that that's what it's going to be. But yes, when these intersect each other, you can work out the math and you can show that this is going to be intersecting at 1, 2, and this point on the right will intersect at 2 and 1. And here's the math in case anybody needs to see it. Where those functions intersect each other, we just take them and we set them equal to each other. Negative x plus 3, because wherever they intersect, that's where the functions are going to have the same values. So multiplying by x will give me 2 to be equal to negative x squared plus 3x. And I can clearly see that this is going to be a quadratic of some kind. So putting it in standard form, I'm going to have x squared minus 3x plus 3 to be equal plus 2 to be equal to 0. And so when I factor it, I'm going to get x minus a 2 and x minus a 1. And that's where you can see that here I get x equals 2, here I get x equals 1, and that's where the interval of 1 to 2 is going to be. So there's my interval. So let me go ahead and change colors here so that everything doesn't kind of blend together. So now we're going to be looking at, now we have the interval, so we're kind of ready to identify what the definite integral for the volume is going to be. But this one, very similar to the example that we saw in the first video, the region is going to be found by essentially two curves, the linear function and the rational function, where that purple region is going to be. And we're going to take the difference of them. So in this case, f of x, the height, so to speak, that we've been looking at for our prism as we kind of unfurled the cylinder, f of x in this case is going to be the difference of the outermost bit, which would be the negative x plus 3, and the innermost part, which is the 2 over x. And that one really doesn't simplify nicely. I'm not going to worry about trying to get a common denominator at this point, but that's what we're going to use for that one part of the dimension there. So here we're going to say volume is equal to, I'm going to just go ahead and put the 2 pi on the outside of the integral. And we are going from 1 to 2. And so now we're going to have x times f of x, which is negative x plus 3 minus 2 over x. And the third dimension is the dx. Simplify the integrand. 1 to 2, and we're going to get a negative x squared plus 3x minus 2, all of it times dx. And the integrand has been simplified as far as it's going to go. So now it's time to take the antiderivative, and I'm going on autopilot there. We don't want to write the definite integral anymore. We're going to take the antiderivative, so this is going to be negative 1/3 x cubed when I take the antiderivative of a negative x squared. And then I'm going to get a positive 3 over 2 x squared for the second term. And the third term's antiderivative will be minus 2x. evaluated from 1 to 2. And at this point here, it just becomes a plug and chug exercise. Now, I don't have a common factor that I can pull out here. And since my lower bound is not a 0, we do have to substitute the 1 when we do the lower bound. So let's see if I can fit all this in here. So we're going to say 2 pi times -1/3 times 2 cubed 3/2, 2 squared minus 2 times 2. And I'm going to just write the other one underneath here because I know I'm not going to fit it there. -1/3 minus a -1/3. Well, times 1 cubed, so it's really just 1, plus 3/2 times 1 squared minus 2 times 1. Okay, so let's see what we wind up getting. So 2 cubed is 8, so I'm going to get -8/3 plus, so 2 squared is 4. 4 divided by 2 is 2, so that'll give me a 6 minus 4 minus, and now here we're going to just have the -1/3 plus 3/2 minus 2. And we will want to get a common denominator for each individual piece, but I'm not going to do that work here. The -8/3 plus 6 minus 4, that's going to simplify ultimately to be a negative -2/3. And then the other bracket that we have there, the -1/3 plus 3/2 minus 2, that'll work out to be a -5/6. So I'm going to say plus 5/6, giving us our volume to be, simplifying the bracket one more time. So we would say it'll be a positive 1/6 when we get a common denominator. And so the volume, in this case, simplifying the 2 and the 6 in the numerator and the denominator, will give me pi/3 for the volume. And that will conclude the material for the lesson on volumes using the shell method. Thank you for watching. Take care, and I hope you guys are well.